Hello everyone and welcome to General Chemistry 101, and today we are going to continue with chapter 8, which is the periodic table. The last thing we talked about is the size of the atom, or the atomic size, of what we call the atomic radii, and this heavily depends on the what we call the effective nuclear charge, or the Z effective. And last time I explained to you how to calculate the Z effective, which is basically it's equal Z, which is the atomic mass minus the number of core electrons. And we showed you that an example of why fluorine is smaller than lithium in size, although fluorine has more electrons. And you can calculate actually the effective charge based on the rule I gave you, and you can tell now why the size decreases as you go from left to right in the periodic table. So this is the periodic table again. As you go from left to right, the Z effective increases and therefore the size decreases. As you go down the group, the Z effective increases, but the size increases though. So here you see that the relationship between Z effective and the size is not always proportionate. The Z effective works to explain the size decrease as you go from left to right. But as you go from top to bottom in the periodic table, as you go down, the size actually increases. That's because you're adding more shells to the nucleus. Now, when we talk about atomic radius, let's exactly explain what I mean by atomic radius, because in quantum mechanics, it says that electrons are distributed. The electrons, they are not actually located in specific locations around the nucleus. They're not rotating around the nucleus, and nothing of that classical physics terms. Rather, the quantum mechanics speaks about the probability of finding the electrons around the nucleus in what we call orbitals, and we defined the orbitals last time to be 90% of the actual size. So what is actually the size? The atom is just too small and the electrons are just too tiny to talk about the small and big. Small and big is just classical terms. Now here we actually define the size. The atomic size can be considered to be as the volume containing about 90% of the total electron density around the nucleus. So that's the first thing. Another thing is that we take the atomic size to be the half the distance between the two nuclei in two adjacent metal atoms or in the atomic atoms. And for example, if you have hydrogen molecule, which is H2, we take the atomic size to be half the radius of the distance d here, which is the distance between the two nuclei. So that is what we call the atomic radius. So you measure that distance between the center of these two nuclei, and you divide by 2. That will be the atomic radius for molecules. For metals they exist in an array of atoms like sodium and iron and so on. So these adjacent atoms, you measure the distance between the two nuclei, and you divide that distance by 2. That will be giving you the atomic radius. This is actually the exact definition of the atomic radius. Now, because the effective nuclear charge, which is Z effective, increases from left to right in a period, the added valence electrons at each step is more strongly attached by the nucleus than the one before. Therefore, the atomic radius is expected to decrease from left to right, from left to right, and this is what I explained in details in my previous lecture. Now, within a group, the atomic size actually increases with the atomic number, and the answer is why, although the Z effective increases. And that's because we are actually adding a new shell here. So as you go down the group, the atomic size increases because of the adding in new shells. The first law is n is equal 1, so you have only one shell. But for the second period, you have n equals 2, and therefore you have 2 shells of electrons and 3 shells and and so forth. And this is why the size of the atom increases, just adding more floors to the building. This is the trend in atomic sizes. You saw with lithium. Lithium is 150 picometer on that. And as you go with the period, the size decreases until you get to fluorine. Fluorine is the smallest one. Now you go back to sodium. Sodium is bigger, much bigger than lithium, and therefore much bigger than fluorine. And you go back, and this is how the trend on the size increases. Reem, could you please turn off your mic? Reem, thank you. So I'm going to repeat this for the sake of recording. So this is the trend in atomic radii here. You start with lithium. Lithium has a size of 150 picometer. The size decreases as you go across the period until fluorine, and fluorine is the smallest element on Earth, as I told you. And then suddenly the size increases too much when you go to sodium, because sodium is the second period. Of course, sodium is bigger than lithium, and therefore bigger than fluorine itself. And this is the trend continues as you see in the table. Now let's try to solve this question and see how does it fit into our understanding. Referring to the period table, arrange the following atoms in order of increasing atomic radius. And we have phosphorus, silicon, and nitrogen. Now this is the period table. So we're looking at silicon, phosphorus, and nitrogen. So we have nitrogen. We have nitrogen here in the second period. We have phosphorus down there, and we have silicon. So basically, to solve this question, it's so straightforward. Nitrogen is the smallest because it's sitting in a different period. So nitrogen is smaller than both phosphorus and silicon. Now the question is if phosphorus is bigger or smaller than silicon. According to the rule, as you go from left to right in the period table, size decreases, and therefore the phosphorus actually is smaller than silicon, and the trend will be nitrogen is smaller than phosphorus, is smaller than silicon. So again here, to arrange elements, you look at the periods first. The periods in the elements in the second period are smaller than the ones underneath. So nitrogen will be the smallest, and then now you want to think about the fight between silicon and phosphorus, which one is smaller. Of course, as you go to the right, the elements, the size decreases, and therefore phosphorus is smaller than silicon. And you can write the answer here. So here nitrogen is smaller than phosphorus is smaller than silicon in size. Now, but you have to watch out for the words in the question. He says atoms of increasing radius. Now, let's remember here that this is increasing and this is decreasing. So increasing, that means from the small to the big. Small to the big, so in this case, yes, this is right. So small, this is the smallest to the biggest. Okay? Smallest to the biggest, so our answer is right. So if you actually write in the exam, silicon is bigger than phosphorus, bigger than nitrogen. Although this answer is right, but it does not fit to the answer of the question, because when you say silicon is bigger than phosphorus, is bigger than nitrogen, the answer is truly right, but this is decreasing order, not increasing order. Okay, that's why this answer is not accepted. Now let's move on to something we call the ionic radius, which is the radius of the ions rather than the neutral atom. Now, this is more important than the atom itself because this is something we can measure by X-ray. Now, luckily that we are gonna follow the same rule for the ionic radius, that the size increases from as you go down and decreases as you go to the right. But we have two rules here that you need to know, that the size of the cation is always smaller than the neutral atom, and the size of the anion is always bigger than the neutral atom. So if you take lithium and fluorine, lithium is much bigger than fluorine because of the reasons we talked about, as you see here. When you make ions of that, lithium loses an electron and becomes Li plus. the fluorine takes an electron and becomes F minus. So always the Li plus, the cation, is smaller than the neutral atom. And you see here from the picture that lithium is smaller than lithium, where the F minus is bigger than fluorine. And that's because in the fluorine you add an electron, so the repulsion increases, okay, and therefore you have a bigger atom. But in the case of lithium, lithium is in group 1. You take an electron out, actually it goes back to the previous period, which is helium. So Li plus is actually isoelectronic with helium, and therefore it is much smaller than the lithium. So this is a general rule here for you to determine the size of the ions. You can see this in the next slide here, that the ions also, as you go down the group, the size increases. As you go from left to right, the size also decreases. Okay. Now, what about ions with different charges? Let's say I want to compare the size of Li plus with K plus with sodium plus. That's all the same charge, which is +1, and therefore I can apply this rule. But what if I need to compare between two ions with different charges, like Li plus and Mg2 plus or Al3 plus or whatever? Now you can only do the comparison if they are isoelectronic, okay? And this is something very important for you. You can compare ion sizes only if they are isoelectronic, okay? And the third rule is that the radii of tripositive ions are smaller than those of dipositive ions and are smaller than unipositive ions. So for example, in the same period, Al3 plus and Mg2 plus and Na plus, as the positive charge increases, the size decreases if they are in the same period. So Al3 plus is actually smaller than Mg2 plus, smaller than Na plus. Now, to explain this, let me show you here in my whiteboard. What does that mean actually when I say isoelectronic? Let's look at the periodic table. Yes. It depends. Let me show you an example. When can you compare and when you cannot? Let's take an example of fluorine and sodium, okay? So sodium is here. It has sodium has 11 electrons, and fluorine has 9 electrons, okay? When I make Na plus, okay, this becomes 2, 8. In other words, that's the old school one. You can make 1s2, the electron configuration 2s2, 2p8, 2p6, which is the same as, if you look at the periodic table, that's actually neon. So this is the same electronic configuration as neon. For the F minus, it has, I just forget to do something here to put the nucleus. So sodium has 11 protons inside, plus, and then 2, and then 8, and that's for Na plus, okay? We are now doing it for the ions. For the F minus, we have 9 protons in the nucleus, and we have 2, and that's F minus, okay? Now 2 and 8, because the F is taking electrons, an extra electron to become also as neon. So this is 1s2, 2s2, 2p6. So the electronic configuration for F minus is this, same as sodium. The only difference between the two is that it's the nucleus, the number of protons. As I told last time, in chemistry, we don't change the number of protons or neither the nuclear. Now the question is, these are isoelectronic themselves. Isoelectronics, that means they have the same number of electrons. Only in this case, you can compare the sizes. Yes, in this case, fluorine and sodium, they are both having the electronic configuration of neon. They have the same electrons, In this case, you can apply the rule of formal charge, of effective charge, and you can say, well, let's calculate that now. In this case, Z effective in this case for sodium, it's equal Z, which is 11, minus core electrons is 2, which is 9. Now Z effective here is equal 9 minus again 2, which is 7. So the Z effective in Na plus is higher than F minus, and therefore we say that Na plus actually is smaller than F minus. And you see this from the picture here. If you can look at the picture, and I'm right in the solution, you see from the picture here that sodium plus is actually smaller than F minus. But you can answer this question much easier by saying that always the size of the cation is smaller than the neutral atom, and the F and the size of the anion is bigger than the neutral atom itself. You can just easily say that sodium is smaller than F minus. So we have 3 rules here when you compare the size of the ions, and I'm going to summarize these rules in order for you not to get confused. So ionic sizes. This is very important. That the X plus is always smaller than X, and X minus is bigger than X. I wish that you understand what I'm talking about here. This is, the cation is smaller than the neutral atom, and the anion is always bigger. Rule number 2 is that you can only do comparison for isoelectronic elements. Okay? And rule number 3 is that for the same element, X, it's clearly that X3 plus is smaller than size than X2 plus and smaller than X plus. It's smaller than X. That's for the same element. If you're talking about, for example, for chromium, chromium 3 plus is smaller than chromium 2 plus, because simply you're taking electron out and becomes smaller. And also you can apply the nuclear charge for that. Okay, so by now we know that how to arrange the size of the ions. Let's talk about this question here, which is, for each of the following pairs, include which one of the 2 species is larger. So the first one is N3 minus or F minus. Well, okay, let's do that. It's talking about N3 minus and F minus. Now N3 minus, N is 7, so N is 7, and F is 9. When you take 3 electrons out, when you add 3 electrons out to the nitrogen, so you have 7 in the bottom, 7 in the nucleus, and you have now 10 electrons. So N3 minus is 10 electrons to 8. The F minus, we did it many times. It's 9 protons in the middle, and you have 2 and 8. So this is isoelectronic. If they are isoelectronic, then you can apply the rule, and the rule says that as you go from left to the right in the periodic table, the size decreases, and therefore you get the F minus is smaller than the N3 minus. So only if they are isoelectronic, you can put the formula, the idea, you can compare between them. Okay? Sure. And to prove that, you can just look at this picture again here. You can tell that F minus has a size of 133, while N3 minus is 171. Okay? So we did that only because of the fact that these guys are isoelectronic. You can compare things with isoelectronic. Now let's move to B. B says Mg2 plus or Ca2 plus is bigger. Now we need to look at the periodic table and just tell which one is higher than the other. Now Mg2 plus is in the second group, and we have Ca2 plus, which is underneath it. Now these guys, they're not isoelectronic, but they are in the same group, and they are ions, so we can apply the rule that the ion sizes increases as you go down, and therefore Ca2 plus is definitely larger than Mg2 plus. And for part C of this question, which says Fe2 plus or Fe3 plus, that's the rule number 3 I told you, for the same element, as the charge increases, of course the size will get smaller, and therefore Fe3 plus is smaller than Fe2 plus. In other words, the Fe2 plus is larger than this. So the answer for A, he says which one is larger? Larger Na3 minus is larger here. And for number B, the calcium, of course, is larger. And for number C, we said that Fe2 plus is the largest. So by this, I finished talking about the size. And I wish you could solve questions from the book. Sometimes the questions are tricky, so please practice this when you do the online quizzes. Now, does anybody have a question about the size? So now going on to the ionization energy, and the ionization energy is defined by, it's the minimum energy in kilojoule per mole required to remove an electron from a gaseous atom in its ground state. So if you take an atom in its gaseous state, let's say argon, okay, you take an electron, that will give you argon plus. Now you need energy to do that, okay, and this is called the first ionization energy. You can apply this to any gases, to any atom, like even sodium. You can gasify sodium, okay? Sodium in the gas phase, one atom. You take an electron to form Na plus in the gas phase plus an electron. This is called ionization energy. You can take one more electron, but that will require a lot of energy, and that's called the second ionization energy. And you can continue on. And generally speaking, the I3 is much higher than I2 and much higher than I1. In fact, I made a mistake. The ionization energy does decrease as you go down because the size increases, and therefore it's easier to remove electrons. Okay, and as you go down from left to right, the size decreases, and therefore it's more difficult to remove electrons. So ionization energy increases as you go down from left to right, and decreases as you go down. It's much easier to remove valence electrons than core electrons. Thus, the larger jump in ionization between the last valence electrons and the first one electrons. And this is the table here. So metal has relatively low ionization energy compared to non-metals because it's easier, right? It's easier to take electrons from them. Let's compare, for example, Na and fluorine. They are in the same period, but Na has only one electron in the outer shell. We can take electron easily, so therefore the ionization energy of that sodium is lower than fluorine, which has none electrons. If you want to take an electron from fluorine, it's really difficult. Now, the ionization energy for oil metalloids generally fall between those of metals and non-metals. Now, the difference in ionization energy suggests that why metals always form cations and non-metals form ions, which makes sense. And the general trend here is that first ionization energy increases from left to right, so it increases from left to right, but there are some irregularities, okay? So before we get into the exceptions, you need to understand that ionization energy, and let's make that clear, the ionization energy actually increases this way. Okay, so these people, they have lower ionization energies, and these people, they're relatively high, have higher ionization energy. To take an electron from an element like neon, it's really difficult, very difficult, because neon is just too small. The electrons are attached to the nucleus, okay, and it's really difficult to remove it. Actually, from fluorine, I think it's most highest ionization energy. Right. Now we have some irregularities in the ionization energy. If you look at this here, you start with hydrogen and you go to helium. Of course, helium has higher ionization energy than hydrogen, and that makes sense because helium has a closed shell. It's difficult to take electrons from it. Now suddenly the ionization energy drops down to lithium, which is in the second period, and the reason of that is lithium is bigger than hydrogen, and therefore it's easier to take electrons from it. And then the energy IE increases. This is the first ionization energy, okay? And energy increases as you go down, as you go across the period, and decreases again, increases. But as you see here, there are some small jumps in the ionization energy. If you look at this, if you look at my mouse here, lithium, the second element, increase and then decrease a little bit, and then increase and decrease. So what's happening? There's something interesting that is happening here that we need to understand. Now, in order to know that, we're almost finished with this chapter actually. Let's think about what's happening in these elements. And this is a nice story that I want to tell you. Let's talk about lithium, beryllium, and boron, which are in the second period. Lithium has 3 electrons in it. It's 1s2, 2s1. Okay? If you want to form lithium plus, you're going to take this electron out, right? So that form, that will form you a 1s2 configuration, just like here. Okay? This is a happy closed shell configuration. That's why lithium would love to go into a lithium plus. The ionization energy of that, it's equal to plus, you can just pull the number from here. The ionization energy for lithium is around 500. That's positive, okay? Because ionization energy is always endothermic. You are paying a price to do that. Now let's go to beryllium, which is the second period after lithium. Beryllium has 4 electrons, which is 1s2, 2s2, and then if you want to take an electron of that, 2 electrons, because you're going to make Ba2 plus. Oh, sorry, I'm doing only the first ionization energy. So you take an electron to make Ba plus, that will give you 1s2, 2s1. That's a very unhappy situation here, because beryllium was kind of closed shell, or half closed shell, 2s2, and you are bringing it to 2s1. The ionization energy here is higher than lithium, which makes sense. Now you are sitting at around 800 for beryllium. So the ionization energy of beryllium is higher because of 2 reasons. First, you are taking an electron from a smaller element. Beryllium is smaller than lithium anyway. Okay, and the second is that you are taking electron from a filled 2s orbital, so you're going to pay a high price for this. So you're expecting for boron, which is the third element after this, which has 5 electrons, you expect this number to grow. But actually something really nice happening. The boron has a lower ionization energy than beryllium. The electronic configuration for the neutral boron atom is 1s2, 2s2, 2p1. If you want to take electron out of this, okay, you are going to form an ion with an electron configuration B plus. Is that 1s2, 2s2. So this is actually a relatively stable configuration. And therefore, the ionization energy for boron, the first ionization energy, is equal, roughly, if you look at the table here, if you look at the graph here, lithium boron, actually it's around 600, not 1,000. So you start with 500 and then 800, you expect the number to grow to 1100 or something. But now suddenly the ionization energy decreases for boron, and that's because forming an ion forming a monovalent ion for boron will get you into a relatively stable configuration of 1s2 to s2, and therefore it's like boron will give you a discount here. He doesn't want you to pay $1,000, he just want to pay you 600. Okay, but if we go to the element after that, which is carbon, so carbon, the jump increases 1,000 and so on. Okay? Now, based on this, you can also explain the second jump. So I'm talking about the first jump here, okay? But I want you, the way I worked on this, I want you to work on the jump between oxygen and nitrogen and tell me why also there's a jump here. There's a small hump here that also can be explained by the same rationale I talked about, okay? And these jumps also repeat themselves across the periodic table. So this is about ionization energy. Now, let's solve this question, and by that we're going to finish this lecture. Which atom should have a lower first ionization energy, oxygen or sulfur? And which atom should have a higher second ionization energy, lithium or beryllium? First of all, let's talk about the first one, oxygen or sulfur. Now, oxygen and sulfur are in the same group, okay? And he's talking about the first ionization energy, yes. So lower first ionization energy. So we agreed that as you go down the group, the size increases, and therefore it's easier to take electrons out, and therefore we're expecting the ionization energy of sulfur to be lower than that of oxygen. And to prove that, we can just look at the values here. We have oxygen ionization energy, first one is 1300, where sulfur is 999, and I am right, the sulfur has lower ionization energy. Now, which one has the highest second ionization energy, lithium or beryllium? So we have lithium and beryllium. Okay, we explained this already in the previous example. We showed you here that lithium has an ionization energy of 500 roughly, because you're taking electron out, you're bringing it to 1s2. Beryllium, you're breaking a relatively stable, and therefore the ionization energy is higher. This is the first explanation. The second explanation is that as you go from left to right of the periodic table, the ionization energy actually increases, and therefore beryllium has a higher one. But now here he's talking about the second ionization energy. And the second ionization energy, we have to think about this in further details here. So lithium is a 3, so which is 1. It's always nice to write the electronic configuration for these guys, 2s1. And therefore, when you want to make a lithium 2+, which is impossible anyway, you're going to make this is 1s1. This is a very unhighly stable thing, okay? So for beryllium 2+, beryllium has 4 electrons. It's 1s2, 2s2. You want to make a beryllium 2+, that's going to give you a configuration of 1s2, which is isoelectronic to helium. So here you see this is a very healthy situation. Why here this is unhealthy? This is very unhealthy situation. And therefore we're expecting the ionization energy, the second ionization energy, okay? We're talking about the second ionization energy. It's the one that taking 2 electrons out of this. We're expecting the ionization energy for beryllium, for the second ionization energy for beryllium to be lower than the second ionization energy for lithium. Okay, just because of this fact. So it's all common sense. It's all about the electronic configuration. You need to solve these problems by writing the electronic configuration and think about the future of these ions when you form them, and which one is more stable or less stable. So you need to practice problems on this, inshallah.